Our next presenter is our first virtual presentation. So let's see if we can cut down on the technical difficulties that I seem to be having. So our next presenter is John Wathen. He's the science advisor for US EPA's Office of Water. And John, you should be able to share your screen, and we should be able to hear you if you unmute.
Okay, I unmuted.
I hear you.
Headed for the screen, Sharon. Okay, there's my presentation. There we go. Third try is the charm. Okay, I'll stop fooling around and get talking here. I'm glad to be appearing at EC 23 today. I hope you will enjoy and appreciate this presentation on the patterns of PFAS occurrence in U.S. river fish as derived from the 1819 National Rivers and Streams Assessment. This presentation is about PFAS compounds in fish fillet, that's muscle tissue, about considerations for monitoring and fish consumption advisories, what compounds occur together in every fish collected and analyzed in this national survey, and something about temporal trends. Trying to it, there we go. This presentation contains the views of the authors, John Healy, Andrea Contreras-Balbuena, and myself, John Wathen, who all collaborated on this analysis. Along with my favorite 26 words, I can say that John, Andrea, and I represent the EPA Office of Water. The river is the Susquehanna in Pennsylvania, looking upstream towards Williamsport. In this presentation, I'm going to give you some background on our progress of assessing PFAS found in river fish samples, figures describing PFAS compound concentrations in sums in samples, observed concentrations of PFAS in fish tissue, and the persistence of certain PFAS compounds over time. These are maps of the sample locations for the 13 to 14 and 18 to 19 National Rivers and Streams assessments. A presentation on the 13 to 14 NRSA with content related to this presentation was given at EC 22 and is available on the website. Our talk today describes the 18 to 19 NRSA with some comparison between the two surveys results. Again, the focus on here is on the patterns of the occurrence of from 1 to 9 individual PFAS compounds with greater than 20% detections, averaging about 5.4 compounds per fish sample. For the 13-14 survey, there were 7 compounds with few and 6 with many detections. The consistency and repeatability of the compounds for PFOS, PFDA, PFUnA, and PFDoA appeared to dominate the system. We observed the same thing in the 18 to 19 analysis, the few and the many detections, but we show more here. We've gone from 13 to 33 analytes with a gain of 3 compounds with substantial detections of now 9 compounds considered here. This slide clearly shows which PFAS compounds occur in fish, and perhaps just as importantly, which do not, and suggests why. Note the pronounced break that occurs between PFOA and PFNA in kind of the left-hand corner of the slide. This break is also between being more soluble with no or minimal detections in fish to lots of blue ink indicating substantial presence in fish. On this next slide, the same numbers are presented in a font size where you can read them instead of viewing the landscape. The focus is on what is in these samples as opposed to what is not in them. Here we show the frequencies of occurrence of the 9 PFAS detected in fish tissue. The slide also details the number of carbon atoms, the gray dots, saturated with green atoms, the green dots, the red oxygen, yellow sulfur, and blue nitrogen dots represent elements found in the functional groups that determine the nature of these compounds, along with the length of their carbon chain and other characteristics. This slide shows the sample locations and depicts the summed concentrations of the 9 PFAS included in this analysis. Symbols are shaded with increasing darkness of green to indicate higher summed concentrations. And we all know that the West is drier than the East, and there are therefore fewer fish and fewer major rivers, but the pattern on the map is also indicative of a history of PFAS use manufacturing, and disposal that has occurred in the eastern half of the country. Please note the color key and in the lower left-hand corner of the map. This slide depicts the total number of compounds as opposed to the concentration in the same samples included in the previous slide. It also reveals a general correlation between these two indices of occurrence. In general, the two qualities, some concentration and the number of compounds, appear to be near proxies of one another, but a second look, presumably taken at your leisure, will highlight differences that may be further addressed a couple of slides down the road here. I'm not going to spend much time on this slide because I don't have any. You might want to come back and look at it later and see how the pseudo nomenclature was applied, and also look at the key on the right. There is more of interest in the next slide, and this slide will be provided to you in the available PDF copy of this presentation. Just remember that what is in the sample defines it. This slide shows the 54 plus variants of PFAS compound combinations occurring in U.S. major river fish. The name of each combination is derived from the letters the compound name contains. The numbers following the combination names, pseudonyms, is the number of occurrences of that combination out of the 228 that fit into the 4 observed categories as depicted on this slide. There's pseudo compounds, just those 4 compounds in there. That's the orange area. Pseudon is the pseudo compounds with PFNA. That's the blueberry colored area. I hope everyone wants ice cream now. 79 samples. PFDoA is pseudo with the PFOSA. That's the raspberry patch. 32 samples. And pseudona, that's the green area. That's 39 samples, included both those 4 compounds plus PFNA and PFOSA. Also down at the bottom, there are some kind of miscellaneous combinations that I call shorts, and they have none of the characteristics of any of the other 4 groups. No pseudo, no PFNA, no PFOSA, no PFNA and PFOSA together. They have the look and feel of leather scraps on the shoe factory floor. It was hard digging into these data, but here's something that we did that I thought was kind of revealing. The data have been sorted here according to how many compounds occurred in a sample, 1 to 9. Then they are ranked by the sum of the PFAS compounds for their compound number group. The maximum number of PFAS, as you might expect, appear generally in the highest concentrations of total PFAS. Samples with less than 6 compounds are more uniform and do not appear to be correlated with the number of compounds in a sample. Whoops. Went up too far. Here we divide this plot up into blue, that's the 1 to 6 compounds, and green, 7 to 9 compounds in the sample. In the 1 to 6 blue half of the world, total concentration by number of compounds rise 1 to 4, and then fall with 5 to 6 compounds. In the 7, 8, 9 compounds per sample green half of this world, the concentrations only rise. To us, this suggests separate mechanisms at work which result in such a bimodal distribution pattern. Moving to another means of displaying sample information, tissue samples with 7, 8, or 9 compounds are abundant, and compound counts may provide a simple basis for advisories. There are 18 full boats, that is, samples with all 9 PFAS occurring in fish. Don't eat those fish. Samples with 4 to 6 compounds generally include all 4 pseudo compounds with the characteristic long-chain PFAS toxicity profiles. These compounds are abundant and pervasive, but are not to be befriended just because they are familiar. Of the 3 additional analytes considered in this presentation, as opposed to the previous one, PFTrDA is the most abundant and most likely to occur with the other 2 newly analyzed longer chain PFAS among R, E, or S constituents of a sample combination. Here we pause and look back at the not very simple occurrence of PFAS. The combinations are repetitive, systematic, and recognizable. The degree of repetition of forms is generally mnemonic and produces memorable pseudonyms recognizable by their length and letter sequences. This exercise has a point. The goal of naming these combinations is to provide a framework for facilitating exposure and risk estimation. The usable nature of the nomenclature makes it easy to apply and include in a calculation sequence along with compound concentrations in fish tissue and their respective toxicities, either determined conventionally or estimated using tools such as the relative potency factor or benchmark dose. Apologies for a slide covered with data, but the illustrations follow. The statistical comparison for this current phase of review using weighted concentration data indicated evidence of both decreases in the sum of concentrations and of the amount of a chemical as well. PFOS in particular had a large magnitude and percentage of change between the two NRSAs, the 13 and the 14. The evidence has indicated a pattern of declines for PFAS compounds over the period, the highest being for PFOS, down 57%, 41% for PFDA, and 32% for PFUnA at the p-value level of less than 0.001 for over a 5-year period. The decline in the statistical strength of the decline is highest for compounds with fewer saturated compounds, with fluorine, that is, and the lowest at less than 20% for PFDoA, the longest chain PFAS determined in both the 13, 14, and 18 and 19 surveys. The declines in PFAS concentration of the primary 4 PFAS compounds discussed in the previous slide are illustrated here. Note the separate 10x scale for PFOS compared to the other compounds, and the declines indicated by the arrows above the blue bars between the two NRSA surveys. So those top 4 declined a lot and proportionally. Percentage declines in concentrations of those 4 compounds, PFOS, PFDA, PFUnA, and PFDoA, are normalized to percentage declines between the two surveys, 13 and 14 and 18 to 19 survey, plotted here against the number of fluorine saturated carbons of these pseudo compounds. Now, this looks like a straight line to me, maybe a little waffle up there with PFAS, but this is showing the proportionality, inverse proportionality between the number of carbons and the degree to which the compounds escape over time. As is apparent on this slide, increasing carbon chain followed the decrease of long chain PFAS solubility down the slope of an asymptotic. Oops, sorry, that's for the next slide. This slide depicts the calculated solubilities of 6 PFAS compounds included in this analysis relative to their respective numbers of F-saturated carbon atoms. The compounds included on this plot encompass the full range of identified substantial PFAS occurrence in fish. Consistent with what we have observed in these samples, the relatively shorter PFAS chain compounds in riverfish, PFOS, PFDA, and PFUnA, are more likely to decline over time relative to compounds with longer chains, such as PFDoA, down at the bottom of the slide. As is apparent on this slide, increasing carbon chain and molecular mass follow the decrease of long chain PFAS solubility down the slope of an asymptotic curve. These compounds are more likely to be retained in the organism, and the more soluble compounds, such as PFOS, are apparently headed for sea level. This is the end of the presentation and the end of the Susquehanna River. Let me just say that PFAS are totally synthetic, not animal or not vegetable in any way, but synthetic halocarbon chemicals. Independent of, but not unrelated to their toxic effects, their occurrence, movement, and form in water, air, and biota are products of their unique chemistry. PFAS persistence, accumulation, and transport are functions of their mass, carbon chain length, and solubility, among other factors. I have acknowledgments to make for this presentation for Mike Dumel, for his vital statistical assistance and extremely helpful in general statistic review from Brian Schnitker. We knew what we needed, but these folks knew how to get it. Also, the data for this project came from the 2018-19 NRSA project team, Leanne Stahl, now retired, Tony Olson, EPA ORD, Blaine Snyder, Tetra Tech, and Harry McCarty from GDIT, and many others. Thank you very much.